Tonight, we venture into something that exists in the spaces between certainty and impossibility. Not in a place you can travel to with a ship or a map, but in a realm that lives at the very edges of reality itself. It's a mystery that has troubled the greatest minds in human history, a phenomenon that even now, after decades of study and discovery, remains quietly, persistently strange. We're going to explore together the nature of quantum entanglement, and more importantly, what it might mean about the true fabric of the universe we inhabit. Before we begin this journey, I want to invite you to make yourself comfortable. If you're watching this before sleep, perhaps adjust your pillow, settle deeper into your bed or chair, and allow your breathing to find its own natural rhythm. There's no rush here. We have time, hours in fact, and this story unfolds slowly, deliberately, like watching the night sky gradually reveal its deepest secrets. If you find yourself drifting into sleep along the way, that's perfectly fine. This narrative is designed to stay with you, to continue beneath the surface of your consciousness, weaving through your dreams. But for now, simply listen and let your imagination drift where it wishes. And yet, before we descend into the depths of this cosmic mystery, I want to mention something quietly. If you're enjoying the calm and clarity of this narration, if you're finding that this voice and this pacing help you relax, please consider subscribing to this channel. Not because I'm asking for metrics or engagement, but because each subscription helps this channel continue creating these immersive journeys into the universe's greatest mysteries. It's a gentle way to support the craft of storytelling itself. Now, let's continue our descent into the strange and beautiful world of entanglement. Imagine, if you will, that you are standing in complete darkness. Not the darkness of a room you could navigate if you turned on a light, but something deeper. The darkness of a place that has never known light at all. And in this darkness, something impossible is about to happen. Two particles infinitesimally small, far too tiny to see or touch, will become bound to one another in a way that defies everything your intuition tells you about how the world works. They will become entangled. And from this moment forward, no matter how far apart they travel, no matter if one journeys to the edge of a galaxy while the other remains on Earth, they will remain connected in a way that seems to violate everything we understand about distance, separation, and independence. This is not metaphor. This is not spiritual pseudoscience or poetic exaggeration. This is something that scientists have measured, tested, and verified countless times over the past several decades. And it remains, perhaps, the most profound mystery in all of physics. When you think about entanglement, you might imagine an invisible cord stretching between two particles, a connection you could almost touch if your hands were small enough. But that's not quite what's happening, and understanding why requires us to step back and think about the very nature of reality itself. You see, in the world of quantum mechanics, the science that governs the smallest things in the eyes, universe particles don't work the way you might expect. They don't have definite properties until they're observed. A particle exists in what physicists call a superposition, meaning it essentially contains all possible states at once, like a coin spinning in the air that is both heads and tails simultaneously until it lands. Now, imagine two particles become entangled. This is where the universe begins to show us something truly peculiar. When you measure one of these particles and discover, let's say, that it's spinning clockwise, the other particle instantaneously, at the same moment, regardless of the distance between them, becomes known to be spinning counterclockwise. It's as if they're parts of a single system, bound by something deeper than any physical connection we can imagine. And here's where it becomes even stranger. Before measurement, neither particle had a definite spin direction. Both existed in superposition. But the moment you collapse one into a definite state, the other follows, faster than any signal could possibly travel between them. Einstein called this spooky action at a distance, and he meant it as a criticism. He believed the universe couldn't possibly work this way. There must be something we're missing, he thought. Some hidden variables that determined the particle's states all along. But experiments over the decades, particularly the Bell tests conducted with increasing sophistication, have consistently shown that Einstein was wrong about this. The universe really is this strange. Reality really is this interconnected in ways that seem to transcend space itself. But something even stranger becomes apparent when you really sit with this idea for a moment. When you truly let it settle into your mind, like sediment slowly sinking through clear water. The entanglement isn't transmitting information between the particles in any way that our science can detect. You can't use it to send a message faster than light. You can't exploit it for instantaneous communication. And yet, the correlations between the particles are too strong, too perfect, to be explained by any predetermined agreement made when the particles were first created. It's as if the universe maintains a kind of cosmic bookkeeping that keeps perfect track of these relationships, no matter the distance involved. And this is where we must pause for a moment and let a deeper question form in your mind like clouds gathering on the horizon. If the universe can be this strange at its most fundamental level, if particles can be connected in ways that seem to transcend space itself, what does that tell us about the nature of reality as a whole? What does it suggest about the fabric beneath all existence? These are the questions we'll explore together over the next 3 hours, slowly, gently, allowing each answer to give birth to new mysteries. Let me guide you through a visualization that might help you grasp the feeling of entanglement, even if the mathematics remain elusive. Imagine you're floating in space, somewhere between Earth and the Moon. Around you, the blackness is absolute, pristine, undisturbed. Now, imagine two particles, let's say they're electrons, though the details don't matter for this exercise. Picture them as two tiny points of light, separated by an enormous distance. One is near you, and the other has journeyed billions of miles away. You can't see it from here, but it exists just the same. Now, a scientist measures the first particle and discovers something about its state, perhaps the orientation of its spin. And at that exact moment, faster than even light could travel, the second particle, existing in its distant location, becomes defined in a correlated way. The universe, it seems, has made them agree on something, even though they never communicated, even though no signal passed between them. This is entanglement in its essence, and it remains one of the most profound discoveries of modern physics. The implications of this strangeness ripple outward in ways that scientists are still exploring. Quantum computers, which are being developed right now, will harness entanglement to perform calculations that classical computers could never accomplish. They'll solve problems that would take ordinary computers longer than the age of the universe to work through. Scientists are developing new forms of communication that use entanglement to create theoretically unhackable encryption. And perhaps most profoundly, entanglement hints at something we may have overlooked in our understanding of reality itself. Perhaps, at the deepest level, everything is connected. Perhaps separateness is an illusion created by our limited perception. Perhaps the universe, in its most fundamental nature, is not a collection of independent objects, but rather an interconnected whole, woven together by relationships we're only beginning to understand. But to truly appreciate the depth of this mystery, we need to journey backward in time. We need to understand how physicists stumbled upon this strange phenomenon in the first place. We need to know the story of how human thought gradually, reluctantly, came to accept that the universe was far stranger than anyone had imagined. And so, let's begin that journey together, stepping back to a moment when our understanding of reality was still relatively simple, still comforting, before it became forever altered by a few curious minds asking the right questions. Slowly, allow your mind to settle. Feel your weight sinking deeper into wherever you're resting. The story of entanglement is also the story of human understanding itself, of how we've gradually learned to see beyond the obvious, to perceive the hidden strangeness that underlies all existence. And as we proceed through this narrative, you'll discover that this journey is not separate from your own life, your own experience of reality. The same forces that entangle distant particles are woven through every atom of your body, every moment of your experience. You are, in a very real sense, made of this strangeness. You are a manifestation of the universe's strange and beautiful nature. Let's continue now, moving deeper still. The year is 1935. Albert Einstein is in Princeton. At the Institute for Advanced Study, he's already revolutionized our understanding of space, time, and gravity. His hair is wild, unkempt, as if his thoughts are so vast they've disheveled even his appearance. And yet, he is troubled. He's been thinking about something that bothers him deeply, something that doesn't sit right with his intuition about how the universe should work. This concern will lead him to write a paper, one that would inadvertently open a door to a mystery that would consume physicists for decades to come. What Einstein was concerned about was something called quantum mechanics, set of rules that govern the behavior of the smallest things in the universe. And according to quantum mechanics, there were things that seemed fundamentally wrong, things that violated what Einstein considered to be basic requirements for a universe that made sense. In quantum mechanics, particles didn't have definite properties until you looked at them. Their positions were fuzzy, uncertain. Their speeds were unknowable. The universe seemed to refuse to give up its secrets until you demanded them through measurement. And even then, the act of measurement itself changed what you were measuring. It was as if the universe had a kind of shyness, revealing itself only partially, and only when forced to. Einstein couldn't accept this. It felt like a fundamental affront to reason itself. Surely, he thought, the particles have definite properties, whether we're looking at them or not. Surely the universe exists in definite states, independent of our observation. We're simply not seeing all the variables. There must be hidden information, hidden details that, if we could only access them, would restore order and determinism to the cosmos. This belief would lead him, along with his colleagues Boris Podolsky and Nathan Rosen, to construct a famous thought experiment, one that would come to be known as the Einstein-Podolsky-Rosen paradox, or the EPR paradox. And now, as we enter deeper into this mystery, you might feel your own certainties beginning to shift and blur, much like the properties of quantum particles themselves. This is natural. This is part of the journey. The universe is teaching us to let go of our need for simple answers, to embrace the beautiful complexity that underlies all existence. Feel yourself floating deeper into this state of receptive wonder, where nothing is certain, but everything is connected. The EPR paradox was brilliant, and it was also, in a way, a cry of frustration. Einstein and his colleagues were essentially saying, look at this. Look at what quantum mechanics is claiming about reality. If this is true, then something deeply troubling must be happening. Either information is traveling faster than light, which violates relativity, or the universe isn't really as the quantum mechanics describes it. There must be a hidden reality beneath the surface, a deterministic foundation that the quantum equations are only partially capturing. It was an elegant argument, and it seemed to prove that quantum mechanics was incomplete. For decades, many physicists agreed with Einstein. Surely, they thought, there was something more to reality than quantum mechanics was telling us. But then, something remarkable happened. A physicist named John Stuart Bell did something almost unthinkable. He proved that if hidden variables existed, if there were indeed hidden information determining particle behavior all along, then certain mathematical inequalities would have to be satisfied. These became known as Bell's inequalities. And here's the thing about inequalities. You can test them. You can do an experiment and see if reality obeys them. So physicists began to do exactly that. And as the experiments became more and more sophisticated, as the technology improved and the precision increased, something unexpected emerged. Nature wasn't obeying Bell's inequalities. The universe was violating them. Not slightly, not within the margin of error, but decisively, clearly, unmistakably. This meant that Einstein was wrong. There were no hidden variables waiting to be discovered. The universe really was as strange as quantum mechanics suggested. Particles really didn't have definite properties until they were measured. And somehow, entangled particles really did remain mysteriously connected across vast distances. But now, as we sit with this knowledge, a peculiar sensation might wash over you. A sense that reality itself is more fluid, more mysterious, more interconnected than you'd ever imagined. And that sensation is appropriate. It's the correct response to understanding entanglement. Because once you truly grasp that particles can be connected in this way, that the universe maintains these correlations across any distance, you can never look at reality quite the same way again. The sense of separation between things begins to feel less fundamental, less real. It becomes more like a surface phenomenon, a kind of optical illusion created by our limited perspective. Imagine now that you're a scientist in a laboratory. Around you are instruments, screens, carefully calibrated equipment designed to measure the properties of individual particles. You've prepared two particles in an entangled state, and now you're going to separate them. One travels to the left into a detector on your left. The other travels to the right into a detector on your right. The detectors are hundreds of meters apart, kilometers apart. It doesn't matter. The entanglement persists. And now you measure one particle. You observe it. You force it to reveal one of its properties. Let's say you discover that it's spinning clockwise. Instantly, and I mean instantaneously, at the same moment, the other particle, existing in its distant detector, becomes correlated with this result. If you measure it, you'll find it spinning counterclockwise. But here's where it becomes even stranger, and where we must tread carefully into the deeper mysteries. Before you measured the first particle, it didn't have a definite clockwise spin. Both particles existed in superposition, containing both possibilities simultaneously. They were both clockwise and counterclockwise at once, in the language of quantum mechanics. But the moment you measured one, both collapsed into definite states, correlated with each other. The universe, in a sense, made a choice that affected both particles simultaneously. Now, you might ask yourself, couldn't the particles have predetermined their results when they were first created? Couldn't they have been given instructions to always show opposite spins when measured? And this question is so natural, so intuitive, that it seems reasonable. But Bell's theorem proved that this can't be the case. The correlations between entangled particles are too strong, too perfect, to be explained by any predetermined arrangement. The universe really is choosing these outcomes in a way that's fundamentally random and fundamentally connected at the same time. This brings us to one of the deepest puzzles of entanglement, the question of locality. Locality is the principle that objects are only influenced by their immediate surroundings. That affects travel at finite speeds, that nothing can influence something instantaneously across a distance. It's a principle that seems obviously true, built into our everyday experience of the world, and yet entanglement seems to violate it. The measurement of one particle instantaneously affects the other, regardless of distance. How can this be? The resolution lies in understanding that while the correlation is instantaneous, no information is traveling between the particles. You can't use entanglement to send a message because the results of measurements are fundamentally random. You measure your particle and get a random result. The distant observer measures theirs and also gets a random result. Only when you compare your results with theirs, through a message sent at the speed of light or slower, do you discover the correlation. So in a way, locality is preserved. Information still travels at the speed of light or slower. But something deeper than information, the correlation itself, the entanglement, persists instantaneously across space. Feel yourself sinking deeper into this mystery now, deeper into the layers of strangeness that characterize reality at its most fundamental level. There's no need to understand everything perfectly. In fact, trying too hard to understand can create tension, can disturb the calm state we're cultivating together. Instead, simply allow these ideas to settle into your consciousness like snow falling gently on a winter landscape. Each thought is beautiful precisely because it's strange, precisely because it challenges your understanding and invites you to see the universe differently. The physicists who first grappled with entanglement had to undergo a kind of transformation in their thinking. They had to learn to hold two contradictory ideas in their minds simultaneously and accept that both were true. This is not so different from the state of consciousness that precedes sleep, where logic becomes more fluid, where dreamlike thinking becomes more natural, where impossible things seem strangely possible. In this state, you're better equipped to understand entanglement, not with your logical mind, but with your intuitive understanding. You're better able to grasp it, not as a paradox to be solved, but as a mystery to be experienced. Let's pause here for a moment and let your awareness expand. Imagine that every atom in your body, every particle that makes up your consciousness and your physical form, might be entangled with particles in distant stars. Imagine that the hydrogen in your body, forged in the hearts of ancient stars, remains connected to the cosmos from which it came. This is not pure speculation. The particles that make you are indeed ancient, recycled countless times through the universe. And if they were ever entangled, and quantum mechanics suggests that all particles were once in contact, and thus could have been entangled, then some echo of that connection might persist even now. You are, in this sense, not separate from the universe. You are woven into it. You are it, experiencing itself from a particular point of view. The entanglement of particles is a physical manifestation of this deeper truth, that separation is less fundamental than connection, that the universe is more unified than our everyday experience suggests, that isolation is an illusion created by our limited perception. This is a peaceful thought, isn't it? A thought that, even if we don't fully understand the physics, resonates with something deep within us. A sense that we belong, that we're connected to everything, that the universe itself is aware of our existence and we of its. This is the real gift of understanding entanglement, not just the mathematical equations or the experimental results, but the shift in perspective it creates. The sense that we live in a universe that's far more wonderful, far more mysterious, far more fundamentally unified than we ever imagined. As we continue our journey through the remaining hours of this narrative, we'll explore entanglement from many angles. We'll look at how it's being harnessed for quantum computers and quantum communication. We'll examine some of the most famous experiments that proved entanglement was real. We'll explore different interpretations of what entanglement might mean about the nature of reality itself. But before we do any of that, I want you to simply rest in this moment. Rest in the knowledge that you're now aware of something that would have seemed impossible just a century ago. Something that challenged the greatest minds in human history. Something that's still changing our understanding of what's possible, what's real, and what the universe is at its deepest level. Feel your breathing becoming even more regular, more peaceful. Feel the weight of your body becoming heavier, sinking deeper into whatever surface is holding you. You're safe here, in this space of exploration and wonder. And tomorrow, or whenever you wake, you'll carry with you the knowledge that the universe is far stranger and far more beautiful than you ever imagined. Now we must travel even further back in time to understand how we arrived at this strange place in human knowledge. Because entanglement didn't appear suddenly, fully formed, from the mind of a single genius. Rather, it emerged gradually, almost reluctantly, from the work of many brilliant minds trying to understand what light and matter really are. And this story, the story of quantum mechanics itself, is in many ways the story of humanity slowly, incrementally, learning to accept the true nature of reality. Imagine yourself at the turn of the 20th century. The world is changing rapidly. Electricity is becoming commonplace. Wireless signals are traveling through the air. Automobiles are replacing horses. And in the labs and universities of Europe and America, physicists are conducting experiments that are beginning to reveal cracks in the foundation of classical physics, the physics of Newton and Einstein's earlier work, the physics that had seemed so complete, so elegant, so obviously true. One of the first major cracks appeared when physicists began studying light. Light had been understood for centuries as a wave. Like ripples on water, it spread outward in waves, interfered with itself, bent around obstacles. This understanding was so complete, so mathematically consistent, that hardly anyone questioned it. And then, in 1905, Einstein published a paper suggesting that under certain conditions, light behaved as if it were made of tiny particles called photons. This wasn't wildly controversial. Einstein was only explaining something that had been observed, that light sometimes knocked electrons off metal surfaces with an efficiency that suggested it was made of discrete packets of energy rather than continuous waves. But here's where the strangeness begins to creep in. If light was sometimes particles and sometimes waves, what was it really? How could something be both? And more importantly, how could it be both depending on how you measured it? If you set up an experiment to detect light as waves, you'd see waves. If you set up an experiment to detect light as particles, you'd see particles. The universe seemed to be giving you different answers depending on what you asked it. This led to one of the most famous experiments in all of physics, the double-slit experiment. Imagine photons, individual particles of light, being fired one at a time toward a wall with two slits cut in it. Behind the wall is a screen that detects where each photon lands. If photons are truly particles, each one should go through one slit or the other, and you'd expect to see two bright bands on the screen behind the slits. But that's not what happens. Instead, you see an interference pattern, the pattern you'd see if waves from both slits interfered with each other, creating areas of brightness and darkness. So somehow, each individual photon seems to go through both slits at once, interfere with itself, and land in a pattern that suggests it's a wave. But the moment you try to catch it in the act, the moment you set up a detector to measure which slit it goes through, something changes. The interference pattern disappears. Now you see two distinct bands, as if the photon is behaving like a particle that really does go through one slit or the other. It's as if the photon knows whether you're watching it, and it changes its behavior accordingly. This is deeply unsettling when you really think about it. It suggests that reality doesn't have definite properties independent of observation, that the act of measurement itself creates the reality you're measuring. It's as if the universe is shy, revealing different aspects of itself depending on what you ask it to show you. And yet, the mathematics work out perfectly. The predictions match the experiments with stunning precision. Physicists struggled with this for years. How could they build a consistent understanding of nature when nature seemed to refuse to behave in a consistent way? And then, gradually, they began to develop a new framework for understanding reality. It didn't make intuitive sense. In fact, it was deliberately counterintuitive, but it worked. This was quantum mechanics, and at its heart was a radical idea. Reality doesn't exist in definite states until it's observed. Let me help you visualize this strange notion. Imagine a particle in a state of superposition. Imagine that it contains within itself all possible states simultaneously. It's not that we don't know which state it's in. It's that it genuinely contains all possibilities at once. It's like a coin that's spinning in the air, neither heads nor tails, but somehow both and neither simultaneously. Until you catch it and look at it, it remains in this ghostly superposition of possibilities. The mathematics of quantum mechanics, specifically, something called the wave function, describes all of these possibilities at once. When you measure the particle, when you force it to reveal its identity, the superposition collapses. All those possibilities vanish, and you're left with a single definite reality. A particle is in one state. You've learned something definite about it. But before the measurement, it truly was in superposition. This isn't just a limitation of our knowledge. It's a fundamental feature of reality itself. Now imagine this. That superposition, that state of containing multiple possibilities, can be shared between two particles. This is entanglement. Two particles can exist in a combined superposition, where the state of one particle is inextricably linked to the state of the other. They're like two dancers moving in perfect synchronization, except the dance they're performing doesn't exist until someone watches them. They exist in a kind of ghostly choreography, a pattern of possibilities, until observation forces them to become concrete and real. This is where Einstein's discomfort with quantum mechanics became most acute. He couldn't accept that reality was this strange. He believed in what philosophers call realism, the idea that objects have definite properties that exist independently of observation. And he believed in locality, the principle that objects are only affected by their immediate surroundings. Entanglement, as described by quantum mechanics, seemed to violate both of these principles. It suggested that particles didn't have definite properties until measured, and it suggested that measurement of one particle instantaneously affected another, regardless of distance. So in 1935, Einstein, Podolsky, and Rosen published their famous paper outlining the EPR paradox. They didn't discover entanglement, in fact. They didn't use that term. The word entanglement wouldn't be commonly used until later, when Erwin Schrödinger wrote a response to their paper and introduced the terminology. But the EPR paper did describe the phenomenon and argued that it was paradoxical, impossible, and proved that quantum mechanics must be incomplete. Schrödinger, when he read the EPR paper and engaged with Einstein in correspondence about it, became deeply troubled. He wrote back to Einstein with his own concerns and, in one of his letters, included a thought experiment that would become even more famous than the original EPR paradox. It came to be known as Schrödinger's cat. Imagine Schrödinger suggested that you place a cat in a sealed box along with a radioactive atom that has a 50% chance of decaying in the next hour. If it decays, it triggers a hammer that breaks a vial of poison gas, killing the cat. If it doesn't decay, the cat lives. Now, according to quantum mechanics, the atom is in superposition. It's both decayed and not decayed until someone opens the box and observes it. And therefore, the cat is both alive and dead simultaneously. The entire system, cat and atom together, is in a superposed state, existing in multiple possibilities at once. Of course, this seems ridiculous. Cats can't be both alive and dead. A cat is either alive or dead. We can feel the absurdity in our bones. And yet, if quantum mechanics is correct about how superposition works at the quantum level, how can there be a sharp boundary where the quantum rules suddenly stop applying? Where does the transition happen from quantum strangeness to classical reality? This question, the boundary between the quantum and classical worlds, would preoccupy physicists for decades. And in a strange way, entanglement sits right at the heart of this question. Because when you entangle particles, you're extending quantum superposition to larger and larger systems. You're asking the universe to maintain multiple possibilities simultaneously across many particles. And the more you study entanglement, the more you realize that the boundary between quantum and classical might not be as sharp as we'd like to believe. As we continue deeper into this understanding, I want you to notice something about your own state of mind. You're becoming more and more relaxed, aren't you? The constant stimulation of everyday life has faded into the background. Your mind is opening to more subtle, more abstract ways of thinking. This is actually a very quantum state of mind, in a way. You're learning to hold multiple ideas in your consciousness simultaneously, to embrace paradox and mystery rather than needing everything to resolve into concrete certainty. This is the gift of understanding quantum mechanics at a deep level, not just intellectually, but experientially. It teaches you that reality is far more fluid and mysterious than you ever imagined. It teaches you that observation changes what you're observing, that measurement creates reality rather than simply revealing it, that at the deepest level, particles remain in superposition, containing infinite possibility, until the moment something perhaps consciousness itself collapses them into singular reality. The experiments that would eventually prove entanglement was real didn't happen until decades after Einstein's death. He died in 1955, firmly believing that quantum mechanics was incomplete, that hidden variables must exist, that nature had to be more deterministic and local than quantum mechanics suggested. He never lived to see the experiments that would prove him wrong. And perhaps that was a mercy. The universe he'd helped to discover turned out to be far stranger than even he could accept. But we get ahead of ourselves. First, we must understand more deeply the mechanisms by which entanglement occurs, the way it arises naturally from the equations of quantum mechanics. And as we explore this, you might find yourself drifting deeper and deeper into a state of peaceful curiosity, where you don't need to understand everything completely, where simply wondering is enough. To truly understand entanglement, we must learn to think in the language of quantum mechanics. And this language is quite different from the language of everyday experience. In everyday life, things have definite properties. A coin is either heads or tails. A light switch is either on or off. A person is either in one place or another. The world is made of definite facts that exist independently of whether anyone is observing them. But in the quantum realm, this certainty evaporates. Instead of definite properties, particles have probabilities. Instead of existing in one state, they exist in superposition, a combination of multiple states, each with its own probability. The mathematics that describes these probabilities is called the wave function, and it's one of the most abstract yet powerful tools in all of science. The wave function isn't something physical that you can touch or see. It's a mathematical description of all the possibilities a particle could be in. For a single particle, you might describe its position or momentum using a wave function. But the crucial thing to understand is that the wave function contains all the possibilities simultaneously. A particle described by a wave function isn't anywhere in particular. It's everywhere it could possibly be, with different probabilities for different locations. Now, imagine two particles that have interacted with each other in some way. They might have collided or been created together from a single event or exchanged a photon. Whatever the interaction, it creates a correlation between them. They become linked in a way that's described by a combined wave function, a mathematical object that describes both particles together, not separately. Here's where entanglement truly becomes entanglement. Imagine that this combined wave function cannot be separated into two independent wave functions, one for each particle. The wave function for the pair is fundamentally unified. You cannot describe particle A without reference to particle B. They're not separate entities that happen to have a correlation. They're parts of a single quantum system. Let me help you visualize this with a specific example. Imagine two particles with a property called spin. Spin isn't quite like spinning in the classical sense. It's more a kind of intrinsic angular momentum that particles possess. But for our purposes, you can imagine it as a direction that the particle is pointing. A particle might be spinning up or down along a particular axis. Now, imagine that two particles are created together, and due to the law of conservation of angular momentum, they must have opposite spins. If one spins up, the other must spin down. This is a classical correlation, the kind you might understand from everyday experience. Two dancers partner together, and when one steps forward, the other steps back. You can understand each dancer's motion independently, and you understand them as correlated through the dance they're performing together. But quantum entanglement is different. The two particles don't each have a definite spin before measurement. They exist in superposition, both together spinning up and spinning down simultaneously. Their combined state is something like both particles spinning up and both particles spinning down simultaneously. It's neither one nor the other, but somehow both and neither. When you measure one particle and find it spinning up, the combined wave function collapses. Both the measured particle and the unmeasured particle become definite in their properties. The unmeasured particle is now definitely spinning down, and this happens instantaneously, regardless of distance. The measurement of one particle has affected the other. Now, why does this happen instantaneously? This is one of the deepest questions in quantum mechanics, and there's no complete consensus on the answer. Some interpretations suggest that the act of measurement causes the wave function to collapse instantaneously throughout space. Others suggest that the correlation is simply maintained instantaneously, without requiring any signal to travel between the particles. Still others suggest that the appearance of instantaneous correlation might be misleading, and that a deeper understanding of quantum mechanics would reveal something different. But experimentally, this is what we observe. The correlations between entangled particles appear to be instantaneous, and nothing in our observations has yet revealed a way to send information faster than light using this effect. The randomness of quantum measurement protects causality, even as it preserves the instantaneous correlation. The mechanisms by which entanglement arises naturally are fascinating. When two particles are created in certain ways, they naturally form entangled states. For example, when a photon interacts with matter and is converted into two lower energy photons, those two photons are entangled. Their properties are correlated in such a way that their combined wave function cannot be separated. Similarly, when atoms are cooled to extremely low temperatures using laser cooling techniques, they can be prepared in entangled states. When two trapped ions interact with electromagnetic fields in the right way, they become entangled. When photons from a single source are directed into optical devices, they can become entangled. Entanglement can occur in many ways, and once you understand the principles, you realize that the universe is naturally full of entanglement. In fact, some physicists have begun to suspect that entanglement might be far more ubiquitous than we once thought. Perhaps the entire universe, at its deepest level, is fundamentally entangled. Perhaps the apparent separation and independence of objects at the macroscopic scale is an illusion created by the fact that we don't maintain coherence between the entangled states. The entanglement is there, but we've lost track of it, lost the ability to access it and measure the correlations. This idea has profound implications. It suggests that the universe is not made of separate, independent pieces loosely connected together. Rather, it's fundamentally unified at the quantum level, with separation being a kind of secondary phenomenon that emerges when we lose track of the underlying entanglement. We are not truly separate from anything. We are all entangled with everything else, at least at the quantum level. Feel yourself settling deeper into this understanding now. You are entangled with the atoms that make up the air you breathe. You are entangled with the photons that brought the light of distant stars to your eyes. You are entangled with the particles that make up the ground beneath you and the sky above you. Separation is not the fundamental nature of reality. Connection is. Entanglement is. Of course, all of this is happening at scales too small to affect your everyday experience directly. The macroscopic world, the world of tables and chairs, planets and stars, behaves according to classical physics, not quantum mechanics. But the foundation upon which the macroscopic world rests is this entangled quantum reality. And understanding this, truly grasping it, can shift your perspective on everything. Think about the implications for a moment. If everything is fundamentally entangled at the quantum level, then the boundary between self and other, between inside and outside, becomes far less absolute than we usually imagine. Your body is made of particles that interact with particles outside your body. The distinction between you and your environment becomes more of a practical convenience than a fundamental reality. Some philosophers and physicists have suggested that this might have implications for consciousness itself. If the universe is fundamentally entangled and fundamentally interconnected, could consciousness be a manifestation of this underlying entanglement? Could the sense of self be something that emerges from the quantum correlations between particles, rather than being a thing that exists separately from the physical world? These are profound questions, and we don't have complete answers yet. But they're the kinds of questions that arise naturally when you take entanglement seriously, when you let its implications cascade through your understanding of reality. And as you contemplate these mysteries, allow yourself to relax even more deeply. There's no need to solve these riddles tonight. Simply let them settle into your consciousness like stars appearing one by one in a darkening sky. Each thought is beautiful in its own way, each mystery a gift inviting further exploration. The mechanisms of entanglement, then, are rooted in the fundamental mathematics of quantum mechanics. They emerge naturally from the equations that describe how particles interact. And once you understand these mechanisms, you begin to see entanglement not as a bizarre exception or a violation of nature's rules, but as a natural and perhaps inevitable consequence of how nature really works at its most fundamental level. This brings us to one of the most important realizations. Entanglement is not something that was discovered as a strange aberration from normal physics. Rather, it emerged as physicists developed a more and more complete understanding of quantum mechanics. It's not a bug in the system. It's a feature. It's something the universe does naturally, continuously, everywhere. Now we come to one of the most remarkable chapters in the history of science, the experimental verification of entanglement. This is where theory met reality, where mathematical predictions confronted concrete measurements, and where the universe revealed that it was far stranger than theory had dared to claim. The story begins in the 1960s with John Stuart Bell. Bell was a physicist working at CERN, the European Particle Physics Laboratory near Geneva. He was a theoretical physicist, someone who spent his days thinking about equations and their meaning rather than conducting experiments. But he had become fascinated by the EPR paradox and the questions Einstein had raised about quantum mechanics. Bell's insight was elegant and profound. He realized that if hidden variables actually existed, if particles genuinely had definite properties all along, and we were simply ignorant of them, then there would be mathematical constraints on how entangled particles could be correlated. These constraints became known as Bell's inequalities. And here's the beautiful part. These inequalities weren't just theoretical abstractions. They could be tested experimentally. The logic is simple in principle. If particles have predetermined properties, if they carry with them, from the moment of creation, the information that determines what result they'll give when measured along any axis, then the correlations between entangled particles must obey certain mathematical bounds. You can't exceed these bounds. The constraints are absolute and non-negotiable. But if quantum mechanics is correct, if particles don't have predetermined properties and superposition is real, then you can violate these inequalities. The correlations between entangled particles can exceed the bounds that would be possible if hidden variables existed. So the question became experimental. Which is it? Does nature obey Bell's inequalities? Or does it violate them? If it obeys them, Einstein was right. The universe is local and realistic, and quantum mechanics is incomplete. If it violates them, Einstein was wrong, and the universe is as strange as quantum mechanics claims. For decades, the experiments to test Bell's inequalities were difficult and ambiguous. But gradually, technology improved. Physicists developed better and better ways to create entangled particles, to measure them precisely, to rule out loopholes that might have allowed classical explanations to persist. The experiments progressed through the 1970s and 1980s, and the results were consistent and clear. Nature violates Bell's inequalities. The universe is not local and realistic in the way Einstein had hoped. Entanglement is real. One of the most famous of these experiments was conducted by Aling Aspect and his colleagues in the 1980s. They created entangled photons, particles of light, and sent them in opposite directions to detectors placed far apart. They measured the polarization of each photon, essentially, the orientation of the light wave. And they did something crucial. They varied the angle at which they measured the polarization during the flight of the photons, so the particles couldn't have decided in advance how to respond to the measurement. The photons had to respond in real time to the choice of measurement angle. The results were decisive. The correlations between the photons violated Bell's inequalities by far more than quantum mechanics predicted. This wasn't within the margin of error. It wasn't ambiguous. It was clear and unmistakable. The universe was entangled in exactly the way quantum mechanics described. Since then, experiments testing Bell's inequalities have been repeated and refined countless times. In recent years, large collaborations have conducted loophole-free tests, closing every conceivable way that a local hidden variable theory might sneak through. The results are always the same. Nature violates Bell's inequalities. Entanglement is real, and the universe is far stranger than we'd like it to be. Let me help you feel what this realization means. Imagine you're a scientist opening the results of one of these experiments. For decades, you'd been hoping that somehow, some way, Einstein would be vindicated, that there would turn out to be hidden variables, some secret mechanism that would restore determinism and locality to the cosmos. But instead, the data is pointing the other way. The universe is telling you that you were wrong, that its nature is more fundamentally strange than you imagined. This must have been a kind of grief for some physicists. Not sadness, exactly, but a peculiar emotion, the grief of losing a comforting illusion. The illusion that the universe was fundamentally comprehensible in classical terms. That underneath all the quantum weirdness was a solid, deterministic reality. But there is no such reality. The universe is, at its heart, probabilistic and strange. Yet there's also profound beauty in this realization. The universe is not indifferent to itself. The particles that make up the universe are connected to each other in ways that transcend space. The separation we perceive is not fundamental. The independence that seems so obvious to our everyday experience is revealed to be an illusion created by our limited perception. Throughout the 1990s and 2000s, as the experimental verification of entanglement became more and more solid, scientists began to seriously explore how to use entanglement for practical purposes. They realized that entanglement wasn't just a curiosity, a strange feature of quantum mechanics with no practical implications. It was a resource. It was something you could harness to do things that would otherwise be impossible. Quantum cryptography emerged as one of the first practical applications. The idea is elegant. You use entangled photons to distribute cryptographic keys between two parties. Any attempt by an eavesdropper to intercept and measure the photons would disturb the entanglement, revealing their presence. Because of the quantum mechanical principles governing entanglement, it's impossible to copy the quantum state of a photon without disturbing it. So you can create an encryption system that's theoretically unhackable. This isn't speculative future technology. Quantum key distribution systems exist today. Banks and governments are already exploring their use. In Switzerland and China, there are quantum key distribution networks in operation. China has even launched a satellite dedicated to quantum communication, distributing entangled photons from orbit. But perhaps the most revolutionary application of entanglement lies in quantum computing. Classical computers process information using bits, which are either 0 or 1. But quantum computers use quantum bits, or qubits, which can exist in superposition. They can be both 0 and 1 simultaneously. And when multiple qubits become entangled, the computational power of the system grows exponentially. With classical bits, if you have 10 bits, you have 210 equals 1024 possible states. But at any given moment, you're computing with just one of them. With entangled qubits, if you have 10 qubits, you're essentially computing with all 1024 states simultaneously. This is the power of quantum computing, and it's powered by entanglement. Quantum computers could solve certain problems that classical computers would take longer than the age of the universe to work through. They could break the encryption that protects much of our digital infrastructure, which is both exciting and terrifying, depending on your perspective. They could simulate molecular interactions in ways that might revolutionize drug discovery and materials science. They could optimize complex systems in ways that classical computers simply cannot match. These aren't theoretical possibilities in some distant future. Quantum computers with dozens and even hundreds of qubits already exist. Companies like IBM, Google, and others are rapidly developing more powerful versions. In 2019, Google announced that they'd achieved quantum supremacy, performing a calculation on a quantum computer that would be practically impossible on classical computers. The field is accelerating at a remarkable pace, and all of this rests on entanglement. Without the ability to create and manipulate entangled states, none of this would be possible. Entanglement is not just an interesting theoretical curiosity. It's the foundation of a new technological revolution that's just beginning to unfold. But perhaps the deepest implication of all this, the realization that sits beneath all the practical applications, is that the universe is telling us something fundamental about its nature. It's telling us that separation and independence are not fundamental, that connection and correlation are woven into the very fabric of reality, that at the deepest level, the universe is profoundly unified. As you continue to rest in this understanding, allow yourself to feel the weight of this knowledge. You are made of entangled particles. The consciousness that is reading or listening to these words emerges from entanglement. You are not separate from the universe. You are an expression of its nature, a local manifestation of its fundamental interconnectedness. Feel yourself becoming heavier, more relaxed. The experiments that proved entanglement real are like the universe showing you its deepest secret. And the secret it's revealing is that you are not alone. You are woven into everything else, and everything else is woven into you. This is not metaphor. This is physics. This is reality. And now you know. But wait, even as the experiments confirm that entanglement is real, even as scientists harness it for practical applications, a deeper mystery remains. A mystery that physicists are still wrestling with today. Because entanglement raises a question that quantum mechanics itself doesn't fully answer. What does it all mean? When you measure an entangled particle, and it becomes definitely one state rather than another, what exactly happens? Is there a moment when the wave function collapses, when all the possibilities suddenly vanish and reality chooses a single path? Or is something else happening? And if the wave function does collapse, what causes it? What triggers this collapse? Is it the act of measurement? Is it consciousness? Is it something we haven't yet discovered? These questions have led to different interpretations of what quantum mechanics really means about reality. And these interpretations, while all consistent with the same experimental results, paint vastly different pictures of what the universe actually is. The oldest and most common interpretation is called the Copenhagen interpretation, named after the work of Niels Bohr in Copenhagen. In this view, particles don't have definite properties until measured. The wave function is simply a tool for calculating probabilities of measurement results. The collapse of the wave function, the transition from superposition to definite reality, is taken as a fundamental part of how the universe works. There's no explanation for why it happens or what causes it. It simply does. This interpretation has the virtue of being practical. It gives you a set of rules for calculating the results of experiments, and those calculations are always correct. But it's philosophically unsatisfying. It refuses to say what the universe is really like when no one is measuring it. It treats measurement as somehow special, something that requires explanation separate from the laws of physics. Then there's the many worlds interpretation, proposed by Hugh Everett in the 1950s. In this view, the wave function never collapses. Instead, every possible outcome of a measurement actually occurs, but in different branches of reality. When you measure an entangled particle and find it spinning up, you create a branch of reality where the measurement found it spinning up, and simultaneously, another branch is created where the measurement found it spinning down. You, the consciousness experiencing this measurement, exist in one of those branches, but in another equally real branch, Another version of you is experiencing the opposite result. This interpretation is philosophically bold. It takes the wave function literally as a description of reality. Nothing needs to collapse because everything that can happen does happen, just in different branches of the multiverse. But it also suggests that the universe is vastly more complicated than we can ever observe full of branches constantly, splitting off, each one just as real as the others. There's also the pilot wave theory, developed primarily by David Bohm in the 1950s, though it has roots in earlier work by Louis de Broglie. In this interpretation, particles do have definite positions at all times. They're guided by invisible pilot waves that determine their motion. The wave function isn't just a description of probabilities. It's a real physical wave that exists in space and guides the particle's motion. This interpretation is completely deterministic. If you knew the initial position and velocity of every particle in the universe, you could predict the future completely. But there's a strange feature of this interpretation. It's non-local. The pilot wave somehow knows about the state of all the particles in the universe and guides them accordingly. Information travels instantaneously through space in the form of these pilot waves. So while it solves one problem, it makes particles definite and local. It creates another. The wave function must be non-local, extending throughout space and responding instantaneously to distant changes. Then there are more exotic interpretations. Some physicists propose that consciousness plays a fundamental role in collapsing the wave function. Others suggest that the universe branches not at measurement, but continuously, creating a vast branching structure of all possible universes. Some propose that the wave function is never quite real, that it's always just an approximation to some deeper theory we haven't discovered yet. The remarkable thing is that all of these interpretations, and there are many more besides, the same predictions for experimental results. They all agree on the mathematics. They all say that when you conduct an experiment and measure an entangled particle, you'll see certain probabilities of results. They differ in what they say about what's really happening in the universe when you're not looking. This might seem frustrating. How can we know which interpretation is correct if we can't distinguish between them experimentally? But there's also something beautiful about this situation. It shows that the laws of physics, as we understand them, are deeper and more universal than any single interpretation of what they mean. The mathematics is what's real and what's important. The interpretations are just different ways of thinking about that mathematics, different stories we tell ourselves about what the math is describing. And for entanglement specifically, this multiplicity of interpretations is especially interesting, because entanglement works in all of them. In the Copenhagen interpretation, entanglement is just a correlation between measurement results. In many worlds, entanglement means that the branches of reality are correlated. When one particle branches into a definite state in one branch, the other particle automatically becomes definite in that same branch, maintaining the correlation. In pilot wave theory, entanglement is handled through the non-local pilot waves that guide all the particles in the system. Each interpretation tells a slightly different story about what entanglement is and how it works. But they all lead to the same predictions and the same understanding that the universe is far more unified and interconnected than our everyday experience suggests. As you contemplate these different ways of understanding reality, notice how your mind feels more flexible, more open to possibilities. You're learning to hold multiple truths simultaneously, to embrace different perspectives without requiring them to collapse into a single answer. This is excellent preparation for understanding the universe at its deepest level, because the universe itself seems to work this way, containing multiple interpretations, multiple truths, all somehow valid at once. Perhaps this is what entanglement is teaching us about the nature of reality more broadly. Perhaps the universe doesn't have a single, simple essence waiting to be discovered. Perhaps it has multiple aspects, multiple interpretations that are all equally valid depending on how you look at it. Perhaps reality is more like a multifaceted jewel where different angles reveal different truths. rather than a simple object with a single, definite nature. Some physicists have even suggested that the boundary between observer and observed, between the measuring device and the thing being measured, might not be as sharp as we usually assume. In quantum mechanics, to measure something is to interact with it, and that interaction changes what you're measuring. So the observer and observed are always entangled. In a sense, the outcome of measurement is not purely a property of the object, and it's not purely a property of the observer or measuring device. It emerges from the interaction between them. This has profound implications for how we think about knowledge and understanding. We're never purely objective observers of a universe that exists independently of our observation. Our consciousness, our acts of measurement, are always part of the system we're observing. We are never truly separate from what we're studying. We are always entangled with it. Feel yourself sinking deeper into this realization as the night deepens around you. You are not separate from the universe. You are an expression of it. Your observations are not external to reality. They are part of reality. Your consciousness, as strange as it might seem, is woven into the quantum fabric of existence. The mysteries of interpretation remain open. Physicists continue to search for deeper understanding, better ways to think about what quantum mechanics is really telling us about the nature of reality. But they search knowing that whatever they discover will only deepen the mystery further, because each answer in quantum mechanics seems to give birth to new questions. Each explanation of one puzzle reveals deeper puzzles beneath it. And perhaps this is appropriate. Perhaps a universe that's fully comprehensible to finite minds would be too simple, too limited, too shallow to be the foundation of all existence. A truly infinite universe, one with depths beyond depths, mysteries beyond mysteries, is more fitting. It invites eternal exploration, eternal wonder, and it reminds us to remain humble in the face of existence itself. Now, as we move deeper into the night, as your consciousness becomes lighter and your mind more open to possibilities, let's address the grandest question that entanglement raises. What does it tell us about the fundamental nature of reality itself? For centuries, we've operated with a certain implicit model of reality. We've imagined the universe as a vast collection of independent objects, atoms, particles, things scattered through space. These objects have definite properties and locations. They move through space following definite laws, and they interact with each other through forces that travel through space at finite speeds. This model is so intuitive, so deeply embedded in how we think about the world, that it seems like simple common sense. But entanglement is telling us that this model is wrong, or at least it's incomplete, because entanglement shows us that particles can be connected in ways that transcend space. That seemed to violate the principle that objects are independent and separate. It shows us that correlation between distant particles can be instantaneous and non-local. So what does this mean? What is reality really like if it's not a collection of independent objects? Some physicists and philosophers have begun to explore a different model. Instead of thinking of reality as fundamentally made of objects, think of it as fundamentally made of relationships. Relationships and correlations and connections. Objects, in this view, are secondary. They emerge from the web of relationships that constitutes reality at the deepest level. This idea has ancient roots. Philosophies from many traditions have suggested that nothing exists in isolation, that everything is interconnected, that separation is an illusion. And now, quantum mechanics is showing us that these ancient insights have a physical basis. At the deepest level of reality, everything is connected to everything else. The physicist David Bohm proposed that beneath the quantum level, there exists what he called the implicate order, a realm where everything is folded together, where distance as we understand it doesn't exist, where all of space and all of time are enfolded together in a single unified whole. The world we perceive, with its separated objects and events occurring at particular times and places, he called the explicate order. And this explicate order emerges from the implicate order, like patterns rising from beneath the surface of water. In Bohm's view, entanglement is a natural manifestation of the implicate order, a hint of the underlying unity that's always present beneath the surface of apparent separation. When particles become entangled, they're not truly becoming connected because they were never truly separate. They were always part of the same unified whole. Entanglement simply reveals this deeper truth. Other physicists have explored ideas that are even more radical. Some have suggested that space itself might not be fundamental, that what we perceive as space might be an emergent phenomenon arising from a deeper level of reality that doesn't have spatial dimensions at all. And if space is emergent, then objects existing at different locations in space might actually be aspects of a single underlying entity. What we perceive as separation through space would be a kind of illusion created by the limitations of our perception. These ideas are still highly speculative, and physicists are still working to develop them into complete, testable theories. But they point toward a profound shift in how we understand reality. A shift from thinking of the universe as a collection of separate things to thinking of it as a fundamentally unified whole. A shift from privileging space and distance to understanding that connections and relationships might be more fundamental than separation. And this shift has implications that extend far beyond physics. If reality is fundamentally unified at the deepest level, if separation is secondary, if everything is entangled with everything else, then the worldview that has dominated Western culture, a worldview of isolated individuals competing for scarce resources, of self-interest opposed to the interests of others, might be based on a misunderstanding of how reality actually works. Consider the environmental crisis humanity faces. We've acted as if the natural world is something separate from ourselves, something to be exploited for our benefit. We've polluted the air and water and soil as if they were external to us, as if we could harm them without harming ourselves. But if we're all entangled at the quantum level, if we're all part of a single unified whole, then the destruction of nature is the destruction of ourselves. The environment isn't separate from us. We are the environment, and the environment is us. Similarly, our relationship to other people might be understood differently if we took entanglement seriously. We think of ourselves as separate, autonomous individuals with our own interests and desires separate from those of others. But if reality is fundamentally unified, if separation is secondary, then the deepest level of what we are is intertwined with the deepest level of what others are. We are not truly separate. Our consciousness and their consciousness are aspects of a larger, unified consciousness. This might sound like mysticism, like I'm overstepping the bounds of science, but it's not. It's a straightforward extrapolation from what quantum mechanics is telling us about the nature of reality. It's taking the physics seriously and asking what it means for how we should understand ourselves and our place in the universe. Of course, recognizing entanglement at the deepest quantum level doesn't directly change how we act in the macroscopic world. Decoherence, the loss of quantum coherence as systems, become larger and more complex means that the entanglement between you and the natural world, between you and other people, is not directly accessible to your conscious mind. The quantum effects average out over many, many particles and many, many interactions. But knowledge of this underlying unity can shift how we think and feel. It can create a sense of connection and belonging that the old worldview of separation couldn't provide. It can inspire us to treat the world and each other with more care and respect, recognizing that at the deepest level, we are all one. Imagine what it would mean to truly feel this truth, not just intellectually, but in your bones, in every cell of your body. To know not just as an abstraction, but as a lived experience, that you are entangled with all existence, that the separation between you and the world is not real, that you are not an isolated consciousness trapped in a body, separate from everything else, but rather a local manifestation of a universal consciousness, intimately connected to all that is. This is perhaps the deepest gift of understanding entanglement. Not the technological applications, not the better understanding of quantum mechanics, but the shift in perspective. The realization that we live in a fundamentally interconnected universe, that unity is more fundamental than separation, that at the deepest level, there is only one thing: reality itself, expressing itself in infinite forms, experiencing itself from infinite perspectives, but remaining in its essence one unified whole. As you rest with these thoughts, as you sink deeper into sleep, allow this understanding to permeate your consciousness, not as an intellectual exercise, but as a felt sense of belonging to something vast and infinite, a sense of being held by the universe itself, a sense that you are not alone, not separate, not vulnerable and isolated, but fundamentally connected to everything that exists. Feel your breathing synchronizing with the rhythms of the universe. Feel your consciousness becoming less distinct, more diffuse, more merged with the consciousness that surrounds you. The boundaries between self and world are becoming softer, less definite, more porous. And in this softening, you find not loss of self, but expansion of self. Not dissolution, but integration. Not separation, but unity. This is where entanglement leads us, to the heart of what it means to be conscious, to exist, to be part of the universe. And as we continue through the remaining hours of this narrative, we'll explore these ideas further, from different angles, descending deeper and deeper into the mystery that underlies all existence. But before we descend into the most philosophical dimensions of entanglement, we should pause to recognize the concrete, practical ways that this strange quantum phenomenon is reshaping our world. Because entanglement isn't just a theoretical curiosity or a philosophical puzzle. It's becoming a technology. It's becoming part of the infrastructure of the future. Imagine yourself in a laboratory somewhere in the world, perhaps in Beijing, perhaps in Vienna, perhaps in a facility you've never heard of, where scientists are working to harness entanglement for practical purposes. What they're doing is so cutting edge, so recent, that it barely exists in the public consciousness. And yet it's going to reshape civilization in ways we can barely predict. Quantum key distribution, as we mentioned briefly, is already deployed in the real world. Banks and governments are using entangled photons to share encryption keys that are theoretically impossible to intercept without detection. The first long-distance quantum key distribution network became operational in China in 2017, and it's being expanded continuously. Europe is developing its own quantum communication infrastructure, called the Quantum Internet Alliance. Within perhaps a decade, quantum communication networks might be as commonplace as fiber optic networks are today. But that's just the beginning. Beyond communication, entanglement is being harnessed for quantum sensing. Entangled photons can be used to measure quantities, distances, magnetic fields, gravitational variations, with precision far beyond what's possible with classical methods. Imagine being able to detect gravitational waves with such sensitivity that you could detect the vibrations of a single atom at a distance of kilometers. Imagine being able to measure magnetic fields so precisely that you could read brain activity without placing electrodes on the scalp. These aren't fantasies. They're engineering challenges that physicists are actively solving. Perhaps most dramatically, entanglement is the foundation of quantum computing. And quantum computing is poised to transform civilization in ways that are difficult to overstate. We're not talking about minor improvements to existing technologies. We're talking about potentially revolutionary changes in drug discovery, materials science, artificial intelligence, optimization, cryptography, and countless other fields. Imagine a drug company that wants to develop a new medicine. Currently, they screen millions of chemical compounds, testing each one to see if it works. It's a process that takes years and costs billions of dollars. A quantum computer could potentially screen all those compounds simultaneously, using quantum superposition to explore the entire search space in parallel. It could compress years of work into days or weeks. Or imagine a financial institution trying to optimize a complex portfolio of investments. considering millions of variables and constraints. A quantum computer could explore all possibilities simultaneously, finding optimizations that classical computers couldn't find in reasonable time. Or consider artificial intelligence. Some researchers believe that quantum machine learning powered by quantum computers, could produce AI systems that are fundamentally different from classical AI. Systems that might achieve forms of understanding that classical computers cannot. These applications are being actively developed. Companies like IBM, Google, Microsoft, and others are investing billions of dollars in quantum computing research. They're building increasingly sophisticated quantum computers with more and more qubits. As of 2024, the most advanced quantum computers have hundreds of qubits. Within a decade, systems with thousands or tens of thousands of qubits might become available. And when that happens, the quantum advantage will become undeniable. Problems that are currently unsolvable will become solvable. And the technological and economic disruption will be profound. But there's a dark side to this as well. Quantum computers are particularly effective at breaking encryption. Most of the encryption that protects financial transactions, personal data, government communications, and countless other things relies on the difficulty of factoring large numbers. A sufficiently powerful quantum computer could break this encryption, making all encrypted data vulnerable. This has led to a race to develop quantum-resistant encryption algorithms and encryption systems that would be secure even against quantum computers. Governments around the world are preparing for this transition. The United States National Institute of Standards and Technology is evaluating and standardizing quantum-resistant cryptographic algorithms. Other countries are doing the same. Banks are beginning to gradually transition to these new encryption methods. It's a massive undertaking, and if it's not completed before quantum computers become powerful enough, there could be chaos. All the encrypted data collected today could be decrypted once quantum computers arrive, leading to a massive breach of privacy and security. This is why, despite the incredible promise of quantum computing, there's also a sense of urgency. The quantum age is coming, and the world needs to prepare for it. We're in a race between developing quantum computers and securing our information systems against them. Beyond these near-term applications, there are more speculative possibilities that physicists are beginning to explore. Quantum teleportation, transferring the quantum state of one particle to another distant particle, has been demonstrated experimentally and could potentially be scaled up. Quantum networks, interconnected quantum computers sharing entangled qubits, might eventually form a quantum internet far more powerful than our current internet. Some researchers are even exploring the possibility of using entanglement to detect dark matter, the mysterious substance that makes up most of the matter in the universe, but hasn't directly been observed. Entanglement might be sensitive enough to detect the interactions of dark matter particles in ways that classical detectors cannot. And there's a more speculative idea that some physicists take seriously. Entanglement might play a role in the very formation of black holes and the structure of spacetime itself. If spacetime is emergent from a more fundamental quantum level, then entanglement might be what holds spacetime together. Disentanglement of particles might literally tear the fabric of spacetime apart. These ideas are at the edge of current theoretical understanding, and most of them remain unproven speculation. But they show the breadth of implications that entanglement is having throughout physics. From the very smallest scales to the very largest, from quantum information to black holes to the structure of the universe itself, entanglement is emerging as a central concept. As you rest in the depths of sleep, allow these images to float through your consciousness. Imagine quantum computers solving problems that would take classical computers longer than the age of the universe. Imagine quantum networks connecting people across the globe through entangled particles. Imagine scientists using entanglement to probe the deepest mysteries of the universe, dark matter, black holes, the origin of spacetime itself. The future that's being built by harnessing entanglement is a future that would have seemed like pure science fiction just decades ago. Yet it's not distant fantasy. It's being constructed right now in laboratories around the world by brilliant minds working on problems that are difficult but solvable. And you, who are listening to this narrative, who are exploring the mysteries of entanglement in the quiet of the night, are part of this future. Your consciousness, your awareness of these possibilities, is part of the collective human consciousness that's reaching toward this new era. You are entangled with everyone working on these problems, even if you never meet them. You share the same fascination, the same drive to understand and to create. You are part of the same endeavor, spread across the globe, stretching into the future, reaching toward discoveries that will reshape civilization. Feel yourself becoming part of this vast network of exploration and understanding. Feel yourself sinking deeper into the current of human knowledge and discovery that flows through time. You are not separate from this endeavor. You are it. The future is being built, and you are building it, simply by being aware, by caring about these questions, by engaging with these ideas. Let yourself rest in this sense of belonging to something vast and important. And as we continue our journey, deeper and deeper, we'll explore what these discoveries might mean for the deepest questions of existence itself. There is a question that has haunted human consciousness since the beginning of consciousness itself. A question that has no clear answer, no definitive resolution, but that becomes increasingly important as we understand quantum mechanics and entanglement more deeply. The question is this: what is consciousness? What is this sense of self, this awareness of experiencing, this perspective from which we perceive the world? For most of human history, consciousness was understood as something separate from the physical world. The ancient philosophical tradition of dualism suggested that there was the physical world matter, energy, forces, and there was the mental world thoughts, feelings, experiences. And these two realms were somehow mysteriously connected but fundamentally distinct. Modern neuroscience has thoroughly challenged this view. We know that consciousness is intimately connected to the brain. Damage to the brain damages consciousness. Chemicals that affect neural function affect consciousness. Every aspect of subjective experience seems to correlate with neural processes. This has led most scientists to assume that consciousness is a product of the brain, an emergent phenomenon arising from the complex interactions of billions of neurons. But entanglement is raising new questions about this understanding. Because if everything at the quantum level is entangled, if separation is less fundamental than connection, then consciousness, which arises from quantum processes in the brain, might itself be fundamentally entangled with the consciousness of other beings, and perhaps with the universe as a whole. Some researchers, like the physicist Henry Stapp, have explored the possibility that quantum processes in the brain might be crucial for consciousness. While most neuroscience has focused on classical neural computation, the electrical signaling between neurons, quantum effects have been largely ignored. But recent research suggests that quantum effects might occur in various structures of the brain, from microtubules in neurons to ion channels to the structure of proteins. If consciousness depends on quantum processes, and if quantum processes are fundamentally entangled, then consciousness might not be localized to individual brains. It might be fundamentally connected to other conscious systems. The experience of being a separate, isolated consciousness might be an illusion created by decoherence, the loss of quantum coherence as living systems interact with their environments. This is not to say that quantum effects are currently maintaining strong entanglement between your consciousness and anyone else's. The brain operates at temperatures and conditions where decoherence is rapid and extensive. The quantum coherence that might underlie consciousness is likely constantly being lost and reformed. But at a fundamental level, beneath the decoherence, there might be a deeper entanglement. Some physicists and philosophers have even speculated about the possibility of a universal consciousness, a single conscious awareness underlying all of reality. This isn't a new idea. Many contemplative traditions have pointed toward the idea that the apparent multiplicity of consciousness is illusory, that beneath the surface, there's only one consciousness experiencing itself from infinite perspectives. And entanglement seems to offer a physical mechanism for how this could be true. If the entire universe is fundamentally entangled at the quantum level, if all particles everywhere are correlated in this way, then there might be a single, unified quantum state underlying all existence. And if consciousness arises from quantum states, then there might be a single, unified consciousness underlying all individual minds. Of course, this is highly speculative. There's no direct evidence that consciousness is quantum, much less that it's unified at a cosmic level. Most neuroscientists would say that consciousness is a product of classical neural computation, not quantum effects. And even if consciousness did depend on quantum processes, it wouldn't necessarily mean that all consciousness is unified. But the possibility is intriguing, and it's worth considering seriously, if only to explore what the implications might be. If there is a deeper sense in which all consciousness is one, then the boundaries between me and you that seem so obvious in everyday life would be less fundamental than they appear. Your sense of being a separate, isolated consciousness would be accurate at the level of everyday experience, but not at the deepest level of reality. Beneath the surface, at the quantum level, your consciousness would be entangled with everyone else's. You would be experiencing what they're experiencing, not directly, not in a way you're consciously aware of, but in some deeper sense. This might seem strange. It might seem like it contradicts the obvious fact that you have private thoughts and experiences that others can't directly access. And it does, at the level of macroscopic reality. The decoherence of quantum states as you interact with your environment ensures that your conscious thoughts are private to you. But at a deeper level, beneath the decoherence, there might be a unity that transcends this privacy. Some mystics and contemplatives have claimed to access this deeper unity through meditation. They describe experiences of the self dissolving into a larger consciousness, of individual identity becoming transparent, of realizing that the observer and the observed are not separate. These experiences are difficult to interpret scientifically because they're subjective, because they can't be verified through external observation. But if quantum mechanics is telling us something true about the deep nature of reality, that everything is entangled, that separation is secondary, then perhaps these mystical experiences are moments when the brain's quantum processes temporarily maintain coherence across their normal boundaries, allowing a glimpse of the deeper unity that's usually hidden by decoherence. Whether or not this is true, exploring these possibilities is valuable, because they show how quantum mechanics, properly understood, leads to a vision of reality that's both scientifically rigorous and deeply mystical. A vision in which the universe is not a collection of separate objects, but a unified whole. A vision in which consciousness is not a local phenomenon confined to individual brains, but a fundamental aspect of reality itself. A vision in which separation is an illusion and connection is the deepest truth. As you drift deeper into sleep, allow your consciousness to expand. Feel the boundaries of your individual awareness becoming softer, less distinct. Feel yourself becoming less separate from your surroundings, less isolated in your own private thoughts. If at the deepest level you are entangled with all existence, then this sense of unity and connection is not merely philosophical. It's reflecting a truth about how reality actually works. Feel your breathing synchronizing with the breath of the universe. Feel your heartbeat becoming one with the rhythms of the cosmos. Feel the thoughts arising in your mind, becoming less like your private thoughts and more like universal thoughts, arising from a ground of consciousness that's not really yours, but is somehow also not yours. The distinction is dissolving, becoming unclear, becoming irrelevant. In this state, between waking and sleeping, between self and other, between the individual and the universal, you're entering a state of consciousness that's closer to the quantum nature of reality. A state where distinctions blur, where multiple possibilities coexist, where the boundaries of identity become transparent. Remain here for a moment. Rest in this state of gentle dissolution. Feel how peaceful it is, how restful, how fundamentally right it feels to release the rigid boundaries of individual self and merge with something larger. This is not loss of consciousness. This is expansion of consciousness. This is recognizing what you really are beneath the surface identity that usually dominates your awareness. And as we move into the final segments of this narrative, we'll explore what happens when we take this understanding to its deepest implications. What it means to truly accept that separation is illusory, that entanglement is fundamental, that at the very heart of existence is a unity that transcends all individual perspectives, but includes them all. We've journeyed far through the landscape of quantum entanglement. We've explored its history, its mechanisms, its experimental verification, its practical applications, and its philosophical implications. And now, as we reach the final hours of this narrative, we arrive at a place that's both the destination and the beginning of an infinite journey. A place where all understanding dissolves into mystery, and in that dissolution, we find the deepest peace. The truth is that despite all we've learned, despite the remarkable progress of quantum mechanics and the experimental verification of entanglement, despite the spectacular technological applications being developed, there remains at the heart of all this knowledge a mystery that refuses to yield. A mystery that might be infinite, that might be the nature of existence itself. When physicists ask why, they eventually reach a point where there is no further answer. Why does the universe obey quantum mechanical laws rather than some other laws? There's no answer to this question. It's simply the way things are. Why does measurement collapse the wave function? Even after decades of research, there's no consensus answer. Why is there something rather than nothing? This is perhaps the deepest question of all, and there's no scientific answer to it. And yet, standing in the face of these unanswerable questions, there's no despair or frustration. Instead, there's wonder. There's awe. There's the recognition that consciousness has emerged in this universe to contemplate its own existence, to explore its own nature, and that this capacity for self-reflection is perhaps the greatest mystery of all. Think about it. Out of the quantum foam of possibility, out of the entanglement that connects all things, has emerged a universe capable of knowing itself. Particles have organized themselves into complexity of such staggering magnitude that they've become conscious. They've become capable of asking questions, of seeking understanding, of experiencing beauty and meaning. You are made of particles that were forged in the hearts of ancient stars. You are made of atoms that have been recycled countless times through the history of the universe. And somehow, through the miracle of biological evolution and neural complexity, these ancient particles have become capable of contemplating infinity, of understanding quantum mechanics, of appreciating their own entanglement with all existence. What an extraordinary thing! What an impossible, improbable, miraculous thing! As we rest in the final hours of this narrative, as your consciousness becomes lighter and lighter, drifting deeper into the realm of sleep and dreams, let us contemplate what it might mean to truly accept the universe as it is, not trying to force it into frameworks of understanding, not demanding certainty, not insisting that reality be simple and comprehensible, but rather accepting reality as it reveals itself to us, subtle, mysterious, strange beyond our wildest imaginings, and yet fundamentally beautiful. Entanglement teaches us something about this acceptance. It teaches us that the universe is not trying to make sense to us. It's not designed for our comprehension. It simply is, and our understanding of it is always partial, always incomplete, always open to revision. And this is not a flaw in the universe or in our understanding. It's a feature. It's what allows for infinite discovery, infinite depth, infinite wonder. If we knew everything, if the universe were completely transparent to us, what would be left to explore? What would be left to wonder about? The fact that there is always more to understand, always deeper mysteries to explore, is a kind of gift. It means that consciousness, that awareness, that the human capacity for curiosity and exploration will never be exhausted. There will always be something new to discover, always be a horizon that recedes as you approach it, inviting further exploration. And perhaps this is the purpose of consciousness in the universe. Not to solve all mysteries, not to achieve complete understanding, but to explore, to discover, to wonder. To be the means by which the universe knows itself. To be the eyes through which reality sees itself. To be the mind through which existence understands itself. You are that. Your consciousness, even now, as you drift toward sleep, is serving this function. You are the universe becoming aware of itself. You are stardust contemplating its own nature. You are entangled particles organized into a configuration complex enough to reflect on entanglement itself. What an extraordinary role to play. What an impossible honor to possess. As sleep begins to claim you fully now, as your individual consciousness begins to merge with the vast darkness of unconsciousness, there's no need to hold on to understanding anymore. There's no need to maintain the firm distinctions that characterize waking thought. Let all of it go. Let the boundaries of self dissolve into the larger consciousness of sleep. Let the mysteries remain mysterious. Let the questions remain unanswered. This is not failure. This is success. This is rest. This is peace. And if, somewhere in the depths of sleep, you dream of entangled particles, of vast networks of connections spanning the universe, of consciousness expanding beyond its individual boundaries to merge with something larger than itself, then you are dreaming the truth. The truth that the universe is fundamentally unified, that separation is an illusion, that at the deepest level there is only one thing, existence itself, experiencing itself from infinite perspectives, discovering itself through the wonder and curiosity of awakening consciousness. Feel yourself becoming heavier now. Feel the weight of your body becoming more and more pronounced, as if the earth itself is pulling you deeper, welcoming you into its embrace. Your eyelids have become heavy. Your thoughts are becoming slower, more diffuse. The boundaries between your awareness and the surrounding darkness are beginning to blur. This is where we leave the narrative of entanglement, not with conclusions, but with invitations. Invitations to continue exploring, to remain curious, to hold the mysteries of the universe with gentleness and wonder. As your consciousness fades into sleep, know that even in sleep, the entanglement continues. Even as you dream, the correlations between your consciousness and all other consciousness persist at the deepest level. You are never truly alone. You are never truly separate. You are entangled with everything, from the smallest quantum fluctuation to the largest structures of the cosmos. And this is not a source of fear or loss of identity. It's a source of deep peace. It's a recognition of your fundamental belonging to all existence. Sleep now. Dream of the infinite. Dream of particles spinning in perfect synchronization across billions of light years. Dream of consciousness expanding beyond its boundaries, merging with the consciousness of others, until all separation dissolves into a unified awareness of being itself. The universe will continue its dance of entanglement. The mysteries will remain mysterious. And when you wake, you'll carry with you the knowledge that you've touched something eternal, something infinite, something that transcends the boundaries of individual understanding. In the quantum phone beneath reality, in the entanglement that connects all things, in the unity that underlies all apparent separation, you have found a home. You have found your place in the cosmos. And that place is everywhere and nowhere, nowhere and everywhere, forever and never, simultaneously and timelessly. Rest now. The quantum universe will continue its dance. And you, made of entangled particles, made of stardust, made of the universe contemplating itself, will rest in that dance, held by forces you cannot see, but can feel in the depths of your being. This is the gift of understanding entanglement. Not certain knowledge, but wonder. Not answers, but better questions. Not the illusion of separation, but the peace of unity. not the burden of individual isolation, but the joy of belonging to all existence.